Last lecture, we talked about pH and pOH. We also discussed that if your hydronium concentration is greater than 1 times 10 to the negative 7 molar, that you're going to get an acidic solution. If your hydroxide concentration is greater than 1 times 10 to the negative 7 molar, then you're going to get a basic solution. A low pH refers to an acidic solution, and a high pH greater than 7 refers to a basic solution. When your concentrations of your hydronium and your hydroxide are equal, and they're equal to 1 times 10 to the negative 7, you get a pH of 7, which is a neutral solution. So it's neither acidic or basic. We also talked about the water ionization constant, which is equal to 1 times 10 to the negative 14 when the temperature of your water is 25 degrees Celsius. And we said that Kw is equal to your hydronium concentration times your hydroxide concentration. Okay, so if we look at this carefully and we take the negative log of both sides, we'll get negative log of Kw is equal to negative log of your hydronium concentration times the negative log of your hydroxide concentration. Okay, so we're going to take the negative log of 1 times 10 to the negative 14, and that's going to equal negative log of your hydronium concentration plus the negative log of your hydroxide concentration. Okay, that's according to your rules for logarithms, that if you multiply them, it's actually, you're taking the summation of that product. And if you plug in your calculator the negative log of 1 times 10 to the negative 14, that's going to equal 14 is equal to, and we know that negative log of hydronium is equal to pH, and the negative log of your hydroxide is equal to pOH. So this is an important formula. 14 is equal to pH plus pOH. So this is another equation that you can use to derive either pH or pOH in some problems. What we're going to look at now is how to determine the pH of a strong acid or a strong base. And if you can recall, a strong acid or a strong base completely dissociates into ions in solution. So let's go ahead and do this example together. We're going to calculate the pH of the strong base barium hydroxide. So if we look at the reaction, the equation for barium hydroxide, when it's placed in water, it's going to dissociate into barium ions and 2 hydroxide ions. So how can we go about calculating our pH here? Well, what we want to do is we want to get our concentration of our hydroxide. And from our concentration of our hydroxide, we would be able to get our pOH, and from our pOH, get our pH. So we know initially we have 0.10 molar of our barium hydroxide. We don't have any barium ions or any hydroxide ions yet because initially they haven't formed. Okay, and since this is a strong base, this is going to completely dissociate. So all of the barium hydroxide will dissociate into ions. So all of this concentration will be used up to form 0.10 molar of our barium ions and 2 times 0.10 molar of our hydroxide ions. So if we go ahead and look at our final concentrations, we have none of the barium hydroxide left, and we have 0.10 molar of our barium ions and 0.20 molar of our hydroxide ions. So we're going to go ahead and use this 0.20 molar of our hydroxide to calculate our pH. Okay, and we know that pOH is negative log of your hydroxide concentration, which in this case is going to be negative log of 0.20. And that ends up being 0.6990 if you plug it into your calculator. So pOH is 0.6990, and we know that pH is going to be 14 minus 0.6990. So that gives us a pH of 13.30, which is what we should expect for something that is a strong base. Now let's go ahead and look at a strong acid such as HCl. We want to calculate the pH. So we know when a strong acid dissociates in solution, there is 100% ions. So what we want to do is use this chart to calculate our final proton concentration and take the negative log of that to get pH. So initially we have 0.025 molar of HCl. We have none of our ions yet initially because they haven't formed yet. And because this is a strong acid, this is going to completely be used up to form 0.025 molar of our proton ions and 0.025 molar of our chloride ions. Okay, so we have none of our HCl molecule. We have 0.025 molar of H plus and 0.025 molar of our Cl minus. So this is pretty straightforward to calculate our pH. We're going to take the negative log of our proton concentration, and that ends up being negative log of 0.025, which ends up giving us a pH of 1.602 for this solution. I also wanted to point out in both these problems the contribution of the autoionization of water into H plus and OH minus is neglected because that concentration when water autoionizes is 1 times 10 to the negative 7, which is very small compared to 0.1 molar or to 0.025 molar.